be positive or negative? Negative, right? How do you know that? Positive times a positive times a negative is negative. So I know it'd be negative here. What about in between these two zeros? Positive, right? Positive times a positive is? Positive times negative? And positive times negative. Right? So even before I've calculated a single point, I know that my function is going to look something like this. Right? That's a big thing that I want you to notice. And Jaquan, I know you can do that. Stop giving up on yourself and being so negative on yourself.
Well, I know that part.
So you know something. So when I give you an understanding check, you can't be like, oh, Mr. Kenny, you might as well not give it to me because I'm going to make a 0. That ain't true. Stop being down on yourself. You're capable of more than you give yourself credit for. But you get negative, and that makes it harder to learn. Huh? I know, you're ready to just graduate and be done, but that's not how life works, unfortunately.
I got 20 days.
Yeah? You got 20 days of great learning in Mr. Kenny's class. That's what I heard.
No.
Yeah. So, activity 4.3. This is where we're picking up. Those of y'all who did not like the distributive property, Xavier, you awake with me? Mr. Gowdy, can you tap him on the shoulder? Because I need you to give me 5 more jumping jacks. I need you staying awake. Thank you, sir. Get that blood moving. Come on, stand up. I'm about to have to make the whole class do it if you don't do it.
Whoa, get up.
Alright. Alright. Okay, you doing push-ups?
Yeah.
Alright, do your push-ups then. Alright, while he's doing his push-ups, alright, we've got the cubic function f of x equals 3x cubed plus 16x squared plus 12x minus 16. That's cubic. How do we know? 3 is the highest degree. Remember, what form is this? Standard form. We all good with that detail? Okay. So we got a standard form cubic function. Then we've got g of x is equal to x plus 2 times 3x minus 2 times x plus 4. We know that's cubic as well because it has what? 3 linear factors, 3 zeros, right? So that's cubic as well. Alright? And the question is, hey, how could we determine if the functions are equivalent? Okay? Where's y'all's stuff?
I got that.
Gotcha. Alright, so I'm not going to go into a lot. Okay? By the way, guys, this is already written up there. I just rewrote it so it's bigger. So I want to point this out. There's a worked example here. We're going to come back to this in just a second. Right now, I want you to focus on question 1. Question 1 says, analyze the worked example for the multiplication of the 3 binomials. I don't even want you to look at that right now. I want us to focus on A, then we'll go back to that worked example. The question on A is, how can you use graphing technology to verify that the expression in factored form, this one, is equivalent to the product written in, by the way, I'm not going to call this standard form, I'm going to call it, or I'm not going to call it general form, I'm calling it what? Standard form, right? So wherever they say general form in the textbook, standard form, okay? So I want you to take 30 seconds just to think on your own and say, hey, what could I do using graphing technology to determine if these two things are equivalent? 30 seconds to think. Go. After that 30 seconds, I'm going to give you time to talk with your group. So 30 seconds now. I say you might want to move back. Ooh.
Are you suggesting?
Well, you need to talk to people in a second, don't you? Well, it's part of your active collaboration. All right, we got 20 seconds down, 10 more to go. Think of a plan. And then you're going to talk with your group and enact that plan. And go. Talk with your small group. Figure out a plan for how we're going to determine if these are equivalent. to listen? You were here when I read those directions out loud. You can't say I'm just now. You thought you were thinking what? So Sheridan, what are you thinking? But look at the question again. It says, how can you use graphing technology to determine if they're equivalent? I mean, it's graphing technology, isn't it? And it's even implying you should do well with that technology. Could you graph them? Let's see what happens when we graph them. Talk to the group. I gotta go talk to other groups. Your group's super intelligent. Talk to them. What's our plan? So graph them both and find the zeros? Okay, so let's graph them both. Let's see what we get. So what do we got? So then do it. Come on. Once you're using graphing technology, right? It says in the question, how can you use graphing technology? Yeah, then do it. I mean, yeah, then do it. You'll come up with a plan, enact that plan. Okay. Activity 4.3, keep going. They're the same? Yep. How do you know? Is it x cubed? No, 3x cubed?
3x cubed plus 16x squared plus 12 plus 16.
X plus 2? So first off, I have to ask, so you'll notice I have both graphs there. Does anyone need me to walk through how to graph both those functions? Yes, sir. You actually need me to, Xavier? Which part of it do you need me to walk you through? Huh? What's the first button you press to do pretty much everything on that calculator, sir? There's one button that we've pushed most of the time to access all the operations.
Hit the little graph button at the bottom.
Once you have a graph open, you need menu, right? Once you go to menu, Xavier, what do you see there that might be really helpful? Graph entry / edit. That's going to help me create a graph?
Yeah.
And what type of graph are we trying to create? A function. So Xavier, you just type in both those equations, bud.
What's a polar?
Don't worry about it. We're not studying it. It's just a different way to look at graphs, but focusing on the radius and the angle to get to those points instead of the x and y coordinates. But the big thing we want to notice is, are they equivalent?
Yes.
How do we know? Those two functions are right on top of each other, right? Notice, and this is a point that I brought up in my other class right here, this is a point. Is that point on both graphs?
Yes.
That means that that point makes both equations what? True. We want to recognize, I don't know exactly what that point is, but that point makes both equations true. This point over here, that's the point, -4, 0, that's a 0. That point makes both equations true, right? And so I also want to point this out, because I don't think I address this very often. What about this point? Does that point make both equations true?
No.
How do we know?
Wow.
I want to push back on that language just a little bit. That's a good idea. It's not on the function, or what's another way we can say it? Well, so what Jaquan said was that point is on the line. And I want to push back on that language just a little bit. You could say that it's not on the curve. Dang it, I just gave it away.
Not on the curve.
It's not on the curve. Remember, that's not a line, that is a curve. Remember, only a line is a line. Only something with a constant additive rate of change can ever be called a line. Otherwise, it's a curve.
Define rate of change.
So it depends on the type of rate of change. So we got constant additive rates of change. We got the constant multiplicative rates of change. We got the linear additive rates of change. We started to learn recently we got quadratic additive rates of change. Hey, what type of function had a quadratic additive rate of change? A cubic. Remember, a quadratic has what rate of change? It needs to be 1 power less, so it's a linear additive. It was the cubics that have the quadratic additives. Alright, so what should we write here under part A? So how can you use graphing technology to verify that the expression in factor form is equivalent?
Plug it into the calculator.
Let's be more clear with that language. Graph both functions. So we don't want to say plug it in because that's not mathematically accurate, but what you're saying, what you're trying to say, Jaquan, and what we would want to say to make it more clear is use the calculator.
You had to write that down in high school?
We didn't have as good of curriculum as y'all do.
How when you went to you said the top 5 best high school in the world, that's what you said.
Okay, one, I didn't say that.
What did you say?
It was the number 5 or it was the number 5 public school in the U.S. When I taught there, not even when I went there. But also, here the issue with looking at it that way is we had a lot of students who worked really hard, and our teachers just assumed we would figure it out.
Oh my God.
So we weren't taught to think like this.
Most are still like that.
Huh?
Most teachers are still like that.
Yeah, I try not to be like that.
That's how you know through it.
And that's why people struggle.
That's what it said, like at Northridge.
Yeah, they don't teach that. Just give it to you, make it
So use the calculator to graph both functions. To see if what? How do we know if they were equivalent?
Because they
Overlap.
match up exactly the same.
They overlap exactly the same. One way we could say it is they map to each other, right? They perfectly overlap.
Which makes the equation true.
There. Well, that means every point makes both equations true, right?
You don't need all that detail.
Yes, you do. Otherwise, you're going to get lost.
I need to see your ACT score man, in the math portion.
What you made, like a 30, 29?
On the math portion?
On the math portion.
On the math portion? Do you actually want to know?
You already told me.
The math portion, I made a 32.
God.
Oh.
So that took it. Overall,
No, that actually is
It
my
should
lowest.
be like a professor, really? In college. Math is your lowest.
Uh-huh.
No way you that's what.
What do you make
Got
on
brain on him, bro.
32, 34, 35, 35.
Okay. Wow. That's
So what was your
Why do you
overall ACT
like
score?
you
34.
So why are you teaching?
Why what?
Why you teaching? Why you not at NASA?
Because we thought this would be more fulfilling to change the curriculum.
Well, not change the curriculum. I wanted to make a difference in students' lives.
You could have been a doctor. Did you know how easy it would be to sit in your house and wait to get a phone call and tell you to show up to a hospital?
Yeah, but this is a different type of making a difference. So, use the calculator. Legitimately, you have to understand, like what y'all are complaining about. Yes, I know that this is more making you think more, but this is what most teachers don't have in the classroom. You were talking about Northridge. So like my undergrad's in civil engineering. When I was doing engineering, I was tutoring a lot of kids from Northridge, which I had always heard was the best school in Tuscaloosa, and I saw how much they were just making kids memorize without actually understanding or thinking or applying, and it frustrated me because all of engineering is thinking. All the careers that my friends that were going into was thinking. It doesn't make sense to just memorize math. It makes sense to learn how to think well and to be clear in your communication of ideas. All the stuff they all complain about, the reason I do it is because that's what's actually going to benefit you long term. It's not what my teachers expected us to do. I'm trying to do better than what my teachers expected us to do. So I'm here because I want to make a difference. But part B. So I use the calculator to graph both functions to see if they map to each other, overlap. And in this case, did they? Yeah. That's how we knew. So how does the cubic function demonstrate the fundamental theorem of algebra?
What does that mean?
That's a great question. Who remembers?
Right. Wait, fundamental.
So, say again.
We asked fundamental.
The fundamental theorem of algebra. What do we mean by that?
The degree is
So, remember, that means that, let's say you have a 4th degree polynomial. What do you know about that 4th degree polynomial?
4 0.
It's got 4 zeros. If you have a 17th degree polynomial, 17 zeros. So let's make it super abstract. If you have an nth degree polynomial, how many zeros are you going to have? Well, it'd be you'd have n zeros. Like a 3rd degree polynomial has how many zeros? You don't say you don't have to say third zeros. You say 3 zeros. If it's 17th degree polynomial, it would have 17 zeros. So an nth degree polynomial would have n zeros. That's all we need. Okay. That's how we make it abstract and applicable in all situations. Yes, sir. Huh? Uh-huh.
I saw one question from this class that was on the ACT.
Not true, because I saw at least 3 or 4 within the first 20 questions.
No, it wasn't.
Yes, it was.
No, it wasn't.
Yeah, it was. Okay. Now, also, I need to clarify, and I want to point out, y'all have to remember, does anyone remember when we finally actually started talking about true Algebra 2 content?
2 weeks ago.
It was after spring break. We've been super behind because let's recognize that COVID wrecked a lot of our educations. I think all of you were in Algebra 1 when COVID hit, correct?
Yeah, correct.
Correct? And then a lot of us missed a lot of school or didn't learn everything we were supposed to do last year.
I was enjoying those little months at the crib.
I'm not in the front. It was nice having time off, right? But it also hurt our education. We've had to cover up or catch up a lot and things like that. All right. So, this 3rd degree polynomial.
I like that. I like that they said 4.
So y'all, right here, we're demonstrating the fundamental theorem of algebra. This 3rd degree polynomial had what? Had 3 zeros. And how did we identify the 3 zeros? We did look at the graph, but even before that, it has 3 what? But how are we get? Look right here. What is actually here?
3.
Yeah, but linear what? Factor. So remember, it's not. And Jaquan, we have to be careful because even if I have something like this, right? So this is. Don't write this down. What degree would this function be?
3.
This would be 3 as well, because this is degree 2 and this is degree 1, right? This is a quadratic times a linear.
Why is it degree 2?
Because of the square, right? That's a quadratic times a linear. So degree 2 times degree 1 gives me degree 3.
You mean?
So we can't.
What's the other ACT?
Well, no, it's more 3x squared times x. Remember how we distributed earlier? That would give me 3x cubed. Because x squared times x is x cubed.
2 times 1 is 2.
So we multiply the exponents
So-
and add them.
Yeah, remember what we're doing is 3x squared times x. How many x's are being multiplied here?
2.
2. Times 1 more x. So how many x's do I have? 3. So we have to recognize that if I have 2 x's, and that's why it's important to understand what those exponents mean. I'm multiplying 2 x's here, multiplying by 1 more, so I have 3. So that's why you can't just say, oh, there's 3 x's. Because right now, if you're looking at it, you might say there's only 2 x's, and that's not true. Does that make sense?
So
So
the exponent one, so that square one there just be two.
that's two of them right there, and there's one more right here.
But if that two on the right there,
It would just be degree 2, yes. And so I will point this out. We don't want to just say factors. A really important word that you put at the beginning of that was what, Preston? Linear, right? The third degree polynomial has 3 linear factors because every linear factor is x to what power? First, right? So it has how many zeros? Right? Every linear factor has a 0, so that's 3 zeros there. Alright. Now, you're going to get some practice on your own in just a second, but I want you to pay attention to this worked example over here. If you like distributing, go for it, right? But what I saw was that a lot of us were struggling a little bit with distributing. So what we have in this worked example, if you want to make a note of this, is it's called the area model for multiplying.
That's what I call real.
The worked example, what's there, is called the area model. Okay. And so I want to clarify and point this out about how this works. If you look under step 1, what does it say? Choose 2 of the binomials to multiply. So, am I ever going to multiply all 3 factors at this same exact time? No. Please, please, please note, I'm only multiplying how many factors at a time? 2. You will only ever multiply 2 factors. Sorry, I just realized I want to make sure that I can get that in the shot. Okay, we're only ever multiplying 2 of those factors at the same exact time. Does it say which factors we do first? So does it matter? It doesn't. They just chose the first 2. So notice they took so they drew out a square. By the way, any guesses why they call this an area model? That, and also literally like it's a box and we're filling in the area of it, right? But yes, this is how you would multiply things for the area. And so I want to point out that, what do they have in this top left-hand corner? Yes, they do. They have a multiplication symbol because we need to indicate what operation we're doing. We are multiplying. And then so they have an x and a 2 here. Why do they have an x and a 2? Why is it x and 2 and not negative x and negative 2? Notice it's x plus 2. Both of those are positive. You okay with that? Right? That's all it is. And then we have a 3x and a negative 2, right? And that's negative because we're subtracting. Now, if I were to distribute, and I just want you to see how these connect. If I were to distribute, I would take this x and multiply it by what? 3x. What's x times this 3x? Then I would take this x and multiply it by negative 2. Hey, what's x times negative 2? Negative 2x. Then I would take my 2 and distribute it to 3x, which would give me, be careful, 2 times 3 is 6. 6x. And then 2 times negative 2 is... So notice, this is just helping me organize my information. And then we want to recognize those like terms. Are there any like terms here? Sorry. Where? Negative 2 and 6x. Now you have to be careful and remember, we multiply the binomials, but for the like terms, what are we doing? But when you say combine, what do you mean? You add them, right? So this x plus 2 times this 3x minus 2 gives me a 3x squared plus 4x minus 4. And notice how I still have an x plus 4 that I need to multiply. But I have two factors. Can I use that area model again with my two factors? I just need 3 terms. So we just continue it from there. It's again going to help you organize your information. Notice when I do this method, I can see in these diagonals my like terms that I'm going to combine. What are your questions about this area model method? Well, if you want to, Jaquan, you can distribute like this and just make sure you never make a mistake. It's your choice. So it's up to you how you want to approach this. However, we're going to quit with football and focus on mathematics, sir. Okay? And so what I want you to see is we're right here on number 2. Pay attention to the order of the work. Determine each product algebraically. Is this, even though it's called an area model, is this algebraic, working with the expressions and the equations?
No.
So what do we mean by algebra? Okay, so remember, algebra is the idea of dealing with our expressions, our equations, inequalities, things like that. So determine each product algebraically. Show all your work, and then use technology to verify your product is correct. What do you think that calculator is? Didn't we literally use the calculator to check them earlier? How about it, right? So we're going to sketch the graph and explain how the function demonstrates the fundamental theorem of algebra. So let me ask you this. You're not going to go into super heavy detail, but I also do not want you to just copy down off the calculator. I want you to think through it. What are the most important points that you should identify from those linear factors to help you sketch the graph?
Zeros.
You need those zeros, those x-intercepts, right? So make sure you pay attention to that and approximate it as well as possible. So work with your small groups. You definitely can work independently for a little bit to use those area models to help you multiply it out, but check in with each other and check in at the very end. What are your questions, concerns, comments before we get started? Let's get to work.